Welcome, and gently find a comfortable place to rest as we drift together into the slow, steady hush of distant stars. Tonight, we linger with the quiet patience of pulsars, the cosmic lighthouses, whose glow does not flash for drama, but hums with the simple rhythm of time itself, gradually fading as the ages pass. If the soft cadence of science helps you unwind, please like this video and subscribe, and feel free to keep the learning flowing by using the playlist link in the description so you can drift deeper and deeper while the story continues in the background. How sleepy are you on a scale of 1 to 10? Imagine yourself settled in a chair that seems to remember your shape, in a room that knows how to be calm. The air is soft, the lights are low, and the world outside feels far away, as if everything beyond these walls has chosen to speak in whispers tonight. Far overhead, beyond the quiet ceiling, and above the roofs and treetops, the sky is wide and steady. There, scattered across the dark like distant campfires, are the cool, unwavering glows of stars. You find yourself tracing a simple line through the night, not searching for constellations or patterns, just allowing your gaze to settle and your breathing to follow its own slow rhythm. Somewhere out there, little beacons sweep the void. They do not hurry. They turn and turn and turn, and in turning, they gently let go of the energy that once moved them with fierce speed. Their patient spin down is our companion, a steady metronome for a drifting mind. Pulsars are small in the way a mountain can be small if you imagine it packed into something the size of a city. A neutron star fits into a sphere perhaps 20 kilometers wide, yet it carries the weight of a star in its dense heart. The matter inside is arranged like a careful library, with layers upon layers pressed so tightly together that atoms have given up their fragile structure. Neutrons, packed close, hold each other in a quiet camaraderie. There is no shouting here, no rush, only the weight of gravity holding things close and the steady rotation that the star remembers from its earlier life. That rotation is the rhythm. It is the heartbeat of the lighthouse. It is the beam that sweeps across space and every so many moments reaches the waiting instruments here on Earth, where it arrives like a clock tick carved from distant air. Imagine sitting beside a gentle radio receiver, the kind that listens rather than speaks. You close your eyes and hear the soft blanket of the sky's background hiss, a quiet like distant rain on leaves. Beneath that texture, there is a pattern, a repeating tap so faint you almost doubt it at first. The taps come at a steady pace, perhaps once every second, perhaps much faster, hundreds of times each second, for the spun-up kind we call millisecond pulsars. If you listen long enough, if you let the sound become a part of the silence, you hear the rhythm. It is not urgent. It is simply there, like a lighthouse on a calm shoreline, sweeping past at even intervals, reminding every passing ship of the curve of the coast. These pulses are the handwriting of a star that refuses to hurry, even as the years take tiny bites from its spin. The classic picture of a pulsar has a quiet beauty. A strong magnetic field threads through the star and out into space, and the star's rotation carries those field lines around, gently combing the surroundings. The poles of the magnetic field are not always aligned with the axis of rotation. As the star turns, so too does the direction of the field's open funnel, where electromagnetic forces guide charged particles to stream outward. This funnel gives rise to a beam of radiation spread out over a cone that traces a slow, reliable sweep. If Earth's line of sight lies in the path of that sweep, we catch each turn as a repeated pulse. We become a shoreline in the path of a calm, patient lighthouse. Spin is energy. For a neutron star, the energy in rotation is stored in the enormous moment of inertia of a compact, dense object turning quickly. Even a period of 1 second is brisk for something so heavy. In the earliest moments after its birth, a neutron star may spin far faster than that, but birth itself is far away in time, and for our purposes tonight, we simply note that the swift beginnings slowly soften. The lighthouse beam reaches us, and the very act of emitting energy, of maintaining a magnetosphere and driving a wind, takes its toll on the star's rotation. There is no drama in this, only the persistent accounting of nature. Every turn gives back a small share of energy. Over long intervals, those shares add up. The spin slows like a top that will never topple completely but prefers a slower dance as the room grows still. Scientists measure this steady fade in ways that are surprisingly tender. The period of the pulsar, the time between pulses, increases very slightly as years go by. The rate at which it increases is calm enough to be written with small numbers, like a whisper of change that only reveals itself over months and years. Period and period derivative, P and P dot, are the simplest words for this. By keeping watch over the timing of pulses, by counting every sweep of the lighthouse beam with patience and care, researchers can trace the slow spiral of energy's release. The star becomes a clock, and we can see time not only within its steady beats, but in the subtle drift of those beats themselves. Imagine yourself listening to a pulsar that ticks exactly once every second. For a while, each tick is the same distance from the next, as regular as a patient heart. Then, over many nights, you find that if you compare these ticks to a perfect metronome, the pulsar lags by the smallest amount. The difference is not obvious right away, but the mind learns the pattern of when to expect the next tick. The slowness, the gentleness of the change is what makes it so pleasing to measure. There is very little surprise here. It is like watching a shadow move across a quiet room at sunset. You do not notice the motion at any single glance, but after a while, the angle has changed, and the room is evening itself. This gentle loss of spin is often explained by magnetic braking. The star is threaded by a strong magnetic field, and as the star turns, the field lines carry energy outward. It is as if the magnet and the turning conspire to create a slow, unhurried break. A simple story often told to get a feeling for this involves a magnetic dipole radiating energy as it rotates, sending power into the void like ripples on a still pond spreading from a careful toss of a pebble. In such a simple picture, the rate at which the period increases follows a law where the spin down depends on the cube of the spin frequency. In practice, the star's environment and magnetosphere refine this picture. The magnetized plasma around the star plays its own role, and the end result is a steady torque. that nudges the rotation slower. If you let your thoughts drift, you might imagine the magnetosphere as a halo of quiet light around the star, drawn out in soft spirals and arcs. Within this region, charged particles ride along magnetic field lines, and there is a point called the light cylinder, where the speed a point would rotate if tethered to the star would reach the speed of light. Inside that boundary, the field lines are tight and organized. Beyond it, they open outward, carrying away a wind of energy that eventually fades into the surrounding space like a breeze that warms the edges of a meadow and then forgets it ever moved at all. This is not a storm. It is a steady, gentle flow, a breath measured on cosmic timescales. The pulses that reach Earth arise in specific zones where charges accelerate along curved magnetic paths. Our instruments catch them mostly as radio waves, though some pulsars shine faintly in X-rays and gamma rays too. Radio pulses are light as air, and they travel through the interstellar medium, crossing a slow ocean of thin gas and dust. Along the way, low-frequency waves are delayed more than high-frequency waves, a phenomenon called dispersion. In a lab, one might speak of dispersion measures and de-dispersion algorithms. But in this quiet room, you can simply picture colors of a sound reaching you at slightly different times, and then imagine us gently restoring them to their proper order, aligning their arrival to hear the true beat hidden inside the blur. The listening itself is the art. The folding of many pulses into a single, clear profile is like knitting soft threads into a blanket. Some pulsars are old and some are young, though those words become stretched when we talk about the lives of stars. A very young pulsar may hum with relatively fast rotation and large spin-down rates, like an eager apprentice that has not yet learned the calm of age. Many tens of thousands of years, or hundreds of thousands, or millions pass, and the rotation slows. The beam sometimes narrows, and eventually some pulsars cross a threshold where our instruments no longer hear them. This threshold has a name in the jargon of the field, but for our purposes, we can just call it the quiet edge. Beyond that line, the lighthouse turns, but its light no longer sweeps across our shore, or perhaps not often enough, or not bright enough to stand out from the hush of background noise. It is not a dark end. It is a fade, gentle and expected. The slow fade can be traced with the idea of a breaking index, a way to describe how the spin-down rate changes with the spin itself. If the star were a simple magnetic dipole in a vacuum, the number would be 3, a tidy value. Observations show that many pulsars have breaking indices somewhat lower than that, which tells us that the magnetosphere, the current systems, and perhaps the evolution of the magnetic field all play parts in the long story. Again, the story is not of sudden changes or clashes. It is more like the weathering of a smooth stone, the slow softening of edges until everything is round and balanced. Observationally, the rhythm of a pulsar is steady enough to serve as a clock, and these stellar clocks have been used to test ideas with a precision that still feels surprising. The discovery there was an observational patience mirrored by the patience of the stars themselves. Early radio astronomers tuned their instruments to catch faint variations in the sky's static, and one of those faint rhythms turned out to be the heartbeat of a pulsar. From then on, the technique has been refined and refined again. Arrays of radio dishes now listen together, leashing far-flung antennas into a single ear. Observers watch for tiny changes in arrival times, for the quiet dance of two stars orbiting each other, for the persistent ripple of gravitational waves bending time like a barely perceptible swell in the ocean of space-time. In these efforts, the calm of the night is the scientist's friend. Noise is a kind of random weather, but the signal grows clearer as you listen long. The beam that we detect is shaped by geometry. The star's magnetic poles and its rotation axis are set at some angle to each other, and the shape of the radio beam follows the geometry of the open magnetic field lines near the polar caps. Our line of sight cuts through that shape in a particular way, and the result is a pulse profile. The profile can be double-peaked or single, wide, or narrow, with a characteristic sweep and polarization that records the stars turning as if our eyes could trace the bow of a dancer. Observe a pulsar long enough, and you may see the profile shift subtly as the star's orientation evolves, or as the magnetospheric state changes. Some pulsars spend time in one mode and then, without ceremony, slip into another. The radio flux grows modestly or fades modestly. Subpulses drift slowly across the profile like a series of lanterns carried past you on a quiet path. This regularity is at the heart of the spin-down story. The lighthouse continues to turn, and its turning is the clock by which we measure the slow loss of energy. The energy goes into the wind, into the particles that are accelerated in the magnetosphere, into the emission we detect, and into the surrounding nebula, if one exists. Some pulsars are embedded in airy veils of wispy gas and magnetic fields, structures that move in slow motion, sculpted by the wind from the star. If you were to glide gently through one of these nebulae like a leaf in a mild current, you might feel as though you were crossing the inside of a diffuse cloud that barely remembers its boundaries. The same spin-down power that kept the lighthouse bright for a time fades into this environment, stitching faint filaments in the night. To help picture the scale of the slow fade, consider the time scales involved. A pulsar may begin its life turning many times per second. As it emits energy, the period increases. After thousands of years, the period might be a second or two, and after millions, perhaps a few seconds. The numbers are not the point so much as the sense that everything here unfolds over spans of time that make a restful night seem instant. The steady torque does not race. It is content to let a million cycles pass before the change becomes noticeable. In the story of the sky, pulsars are patient scribes, adding tiny, regular marks to a long scroll. Imagine yourself in a radio observatory at night. The building lies quiet, the control room lit by soft screens that remind you of jellyfish drifting in a dark sea. Outside, the telescope dish angles itself with slow grace. Each movement measured and smooth. The air is cool. Perhaps there is the faint scent of machine oil and clean electronics, an aroma that suggests order and precision. The instrument listens. Data trickles in like dew forming on leaves. You step gently to the console and see the arrival times of pulses plotted as dots, a tidy row that slowly lengthens, seconds marching like even footsteps. You feel a small relaxation in your shoulders as you watch. Not because the dots are exciting, but because they are calm. Every dot says that the star is still turning, that the lighthouse still sweeps, that the universe remembers its own rhythm. In the background, the interstellar medium quietly shapes the path of radio waves. Thin, dispersed gas adds a slight delay that grows as the frequency lowers. So signals recorded at different frequencies carry a built-in rainbow of arrival teams. Humans learn to correct for this with simple equations and careful calibration. In the mind's eye tonight, you can picture the dial being turned slowly, bringing the slow colors into perfect overlay, and the pulse sharpens like a distant bell heard through open air. A folding algorithm stacks many such pulses on top of each other, like laying many pages of the same poem into a single, bold line. Out of the star's repetitive song, we recover clarity, and with clarity comes the ability to measure the small changes that make the spin down known. There is comfort in measurement. There is a sense that even in a universe that can seem wide and unknowable, certain patterns are trustworthy. Pulsars are among those patterns. They are like metronomes tucked far away on distant shelves, all ticking and slowing in their own ways, all offering a collection of steady notes that can be gathered and used to learn something about the space between us and them. Dispersion measures teach us about the distribution of electrons in the galaxy. Variations in timing reveal whether a pulsar moves in a gentle orbit around a companion, or whether the star itself experiences tiny changes in rotation that might suggest internal dynamics at work. Inside the star, some of that steadiness is set by a superfluid core. It is thought that the neutrons in the deep interior pair up and flow without friction, forming a calm, frictionless pool. The crust above is not perfectly tied to that pool. On rare occasions, the star may adjust itself. The crust could change slightly, or the superfluid could exchange angular momentum with the outer layers, producing a small change in the rotation rate. These events are known by a crisp word, but tonight you can think of them as little hiccups. Tiny, sudden, and then absorbed by the star's ongoing rhythm. Afterward, the slow fade continues as before, as if the lighthouse cleared its throat and carried on with the same long poem. Some pulsars spin very rapidly. These are millisecond pulsars, and they owe their quickness to a long, gentle process of being fed by a companion star. Over periods that may span millions to billions of years, gas from a neighbor can be drawn onto the neutron star, adding angular momentum and slowly shinning the star up. This recycling creates a pulsar with an exceptionally stable rotation. Their pulses arrive with such reliability that they rival atomic clocks. Listening to a whole choir of them at once opens a new way to notice the tiniest stretchings and compressions of time across the galaxy. The idea is that if ripples pass through space-time, they will nudge the rhythm of many pulsars at once, each by a small amount. By comparing the arrival times from dozens of millisecond pulsars spread across the sky, one can seek the common patterns that reveal the presence of those deep, slow waves. Even here, the language is gentle. These waves are at unbelievably low frequencies, changing on time scales of years. They are not a sudden splash. They are like the slow rise and fall of a long swell that a ship at sea might notice only after a day of watching the horizon. Binary pulsars provide another quiet avenue for learning. When two stars orbit each other, their gentle dance causes the pattern of pulse arrival times to sway in and out as the pulsar approaches and recedes from us. The regularity makes it possible to measure the physics of gravity with care. Over time, the orbit itself may shrink slightly as energy is carried away by gravitational waves. The change is tiny, but with years of undisturbed listening, the pattern reveals itself. The dance steps shorten in a way that matches simple predictions from the theory of gravity, a small affirming nod from the universe that the equations are on good terms with reality. Each pulsar you listen to offers a story of geometry and age, of field strength and environment, and of a slow drift through a life cycle. The parameters we track are simple at first glance: period, derivative. Sometimes magnetic field strength estimated from those, sometimes a characteristic age, sometimes an approximate distance inferred from how much dispersion the signal has suffered. All these numbers hang together like beads on a thin string. The star spins, the star slows, and the beam continues its patient sweep. You can imagine each pulsar as a point moving through a space on a diagram, starting in one region and slowly curling toward another, never in a rush. Sometimes the pulsar's beam is not aimed toward us. The galaxy may hold many more lighthouses than we ever see. Those that shine upon us are a sampling of quiet senses of directions and inclinations. Selection biases are a soft phrase for this. We observe what happens to be oriented toward us and what lies within the range of our instruments. As technology improves, we can listen more deeply in wider bands of frequency with better sensitivity and more flexible software. With each advance, we find faint pulsars we had not noticed, and we map the halo of the galaxy with a little more detail, building slow, careful atlases of where the sky's small signals hide. Consider the wind that flows from a pulsar's magnetosphere. Imagine it not as a blast, but as a steady stream, like the outflow of a spring that does not dry, moving outward to mingle eventually with other winds and fields. In some cases, that wind meets a nearby cloud of gas, and the boundary between the two becomes a gently glowing arc, a bow drawn against the medium like the wake of a slow canoe. These faint arcs speak of the star's motion through the galaxy. Many neutron stars travel at significant speeds, gifted with a gentle push long ago that sent them drifting through the night. The wind and the interstellar gas speak to each other at the boundary, shaping and reshaping a delicate structure over thousands of years. Not every pulsar is always active in our radio band. Some go quiet for a while, then return. The reasons are still being explored, but the modes hint at changes in magnetospheric conditions that reorganize the flows of particles, opening and closing the path of emission like a curtain drawn across a window. When the emission stops, the star still spins. When it returns, the clock is there, perhaps shifted a little by subtle torques. The slow fade is patient and continues underneath these changes like a heartbeat beneath the breath. The geometry of the pulsar beam has been modeled with care. The rotating vector model describes how the polarization angle swings through the pulse. And this tells us something about the angle between the rotation axis and the magnetic axis, and about how our line of sight cuts through the radiation cone. Over long times, as the star slowly evolves, there may be a subtle alignment, a soft trend in which the magnetic axis comes closer to the rotation axis. If that happens, the beam would shift away from our view. The spin-down torque might change too. The story remains gentle even here, as the times involved are long and the changes slight. Some studies suggest that the magnetic field experienced in the radio zone, or the effective field relevant to the torque, may itself evolve. Field decay is a phrase used in the literature, but there is no need to picture anything dramatic. Rather, the strengths and configurations adjust over millions of years, perhaps as currents redistribute and fade within the interior and the crust. Perhaps as the star's slow cooling modifies how charges move. Observationally, this leaves the signature we have already discussed, a breaking index that deviates from the simple dipole prediction, and a distribution of period and period derivative values that traces the paths of many stars through the diagram of their lives. You might imagine now a kind of map called the PP dot plane, a simple sketch where each pulsar is a point. Along the bottom axis is the period, and on the vertical axis is the rate at which that period grows. Draw all the pulsars here, and their cloud of points shows how young pulsars cluster in one region and older ones drift in another, how some very fast spinners sit far to the left and low, where their small period and small period derivative reveal their stable, spun-up state. Lines of constant magnetic field strength and lines of constant characteristic age can be drawn across this map, creating a quiet piece of mathematics that helps your mind follow the slow migration. Now, ease back in your chair and allow your breathing to match the pace of the story. The gentle rhythm continues as we drift outward again to the large view of the galaxy and its sprinkling of cosmic clocks. If you prefer, you can picture yourself floating in space far above the galactic plane. The disk below is a gauzy ribbon with bright knots and dark lanes, a softly turning pinwheel of starlight. Moving silently, you find yourself near a pulsar whose beam crosses your path at regular intervals. Each pass is like a nod from an old friend. With each nod, the friend grows a fraction of a fraction slower, and yet never any less steady. This is the essence of patience and the heart of the slow fade. The slow fade is not only in the rotation itself, but also in the luminosity of certain emissions. The available power for high energy radiation and for the wind comes from the rotational energy reservoir. As the star spins down, that reservoir empties little by little. Some young pulsars energize their surroundings with visible structures that shimmer and change on human timescales. As they age and slow, the surroundings grow quieter. There is a balance between the star and its environment, a balance that shifts slowly toward calm. Picture a lantern whose wick is turned down a tiny degree each hour, the flame never flickering, just shrinking so gently that only the most attentive observer can tell. The radio pulses themselves are not simple. They are composed of microstructures and subpulses, and they exhibit polarizations that change across the profile. Yet from a slightly farther perspective, the details blur into a reliable shape. The microstructure is like the tiny fibers in a woven cloth. You can see the pattern if you bring your face very close, but step back, and the cloth resolves into a uniform surface that is pleasant to rest upon. In the same way, for the purposes of sleep, it is enough to know that these fine-grained variations are there, and that they average into regularity over time. An interesting aspect of the spin down is that the torque depends on the alignment between the magnetic axis and the spin axis. If the axes become more aligned over time, the torque may lessen and the spin down rate may decline accordingly. The mechanics are debated and refined, but the notion is simple and soothing. The star smooths its own interior, its own geometry, until in the distant future there is perhaps less difference between the poles and the equator. As far as the magnet is concerned, less difference means less twisting, and less twisting means less breaking. The final state is not a sudden finish line. It is a plateau of quietness. Now, imagine yourself back on Earth, perhaps in a room where a small fan circulates air with a gentle whir. A cup of tea cools by your side. The radio data scrolls on a screen. The pulses continue. Each mark in the record corresponds to a beam that left the star long ago and only now finished the journey to your instrument. If you stack the records from many nights, you can track the slow change in phase that comes from the spin down. The equation that describes it is basic, a series of terms for period and its derivatives, each term smaller than the last. It is like adding steady, simple notes to a musical score. The predicted arrival times match the observed ones to within tiny margins, and those margins become smaller as you refine your timing model, adding corrections for the Earth's motion and for the influence of the interstellar medium. It is a craft, like adjusting a violin until the note is sweet and true. The sweetness here is not bright but cool, the cool satisfaction of order. The surroundings of Earth are also part of the story. As the planet orbits the sun and the observatory rotates with the Earth's surface, the arrival times of pulses must be referred to a common quiet frame, often the barycenter of the solar system. In the soft language of this evening, that is the center of mass of all the planets and the sun taken together. The corrections that bring your times to this frame are computed with ephemerides that carry their own calm, predicting where each body will be with measured confidence. Thus, the spin down you measure is not muddied by the local quirks of our moving vantage point, like placing a book on a table before reading it. This step ensures that what you see is the star's story, and not your own motions reflected back at you over very long intervals. Sometimes a pulsar will be found to change in an unsteady fashion, creating what is called timing noise. The phrase hints at a slight wandering of the star's rotation beyond what a simple model predicts. A mathematician might describe it as a kind of red noise, a slow variation that has more power at low frequencies than at high. But in this gentle account, it is simply a reminder that the interior of a neutron star is complex and alive with processes that we do not yet fully understand. Watching the wander is part of the calm delight of careful observation. It is the lightest of breezes on the surface of a wide lake, barely enough to wrinkle the reflection of the moon. If we lift our gaze outward still to the idea of using pulsars for navigation, the mind can play with a serene vision. Imagine a spacecraft far from Earth, coasting through a region where the sun is a small, bright disk. The craft keeps time by listening to a handful of millisecond pulsars. Each provides a regular tick. And by comparing the arrival times of these ticks to a stored library of expected times, the spacecraft can determine its position without needing to call home. The pulsars become the lighthouses of interplanetary and perhaps interstellar space, a network of steady beacons that guide a ship through the quiet. The technology exists in demonstrative form, and the calm logic of it is pleasing. Pulsars are clocks. Clocks and maps work well together. When you bring them into alignment, you can sail with confidence. Another soft path through this landscape is the exploration of propagation effects. The radio pulses pass through ionized regions whose electron densities vary from place to place. The scattering can broaden the pulse, making its tail gently slope rather than ending sharply. In other cases, interstellar scintillation causes the intensity of the pulse to fluctuate on time scales of minutes to hours, as if the star were twinkling like light seen through ripples on water. We can model these effects and use them to learn about the medium between stars. Even the distortions become instruments of knowledge, giving us extra information about the warm, sparse river through which all light in the galaxy must pass. In the earliest days of studying these stars, the discovery of regular pulses was a surprise. But the surprise has since matured into a field with its own steady stride. Surveys sweep the sky, sifting for patterns that repeat at tightly spaced intervals. And each discovery is checked, timed, and cataloged. Once discovered, a pulsar can be returned to again and again. It does not skip away. It does not play coy. It sits where it is, remote yet dependable, and offers the same story each time you listen, with tiny edits made by the slow fade. A key, their rotational kinetic energy, might be given in simple form, and the rate of energy loss can be estimated from period and period derivative. The numbers that result are large in ordinary terms, but feel measured and modest when placed in cosmic context. The spin-down luminosity for young, energetic pulsars can power nebulous structures. For older pulsars, the power dims, and their surroundings maintain a kind of dignified stillness. That stillness is the place from which the slow fade is easiest to feel. It is a stillness that invites you to soften your focus, to let your eyelids lower, to let the gentle rhythm continue without needing your attention on every beat. Some pulsar beams bring to us not just brightness, but also definite polarization. And by measuring this property, we learn about the magnetic geometry. The angle of polarization sweeps, often in a way that matches the simple expectation of a rotating vector, and this sweep can be fit to infer the path our line of sight takes through the emission cone. The fit is not always perfect, which is as comforting as it is instructive, reminding us that nature is richer than any simplified model. Even in the difference between model and data, there is a kind of quiet music, an invitation to look a little deeper, to adjust the model gently, test it again, and keep the conversation going. As for the interior, models describe layers with evocative names. They speak of a crust, like a lattice of nuclei embedded in a sea of electrons, of a superfluid just beneath, and perhaps of more exotic phases deeper down. Some propose quartets of quarks and other states, but those details need not distract us. What matters is that the interior has properties that allow it to store angular momentum in delicate ways. When the star's outer layers are braked by the magnetospheric torque, the inner reservoir may lag or lead slightly, and at moments it can exchange this angular momentum with the crust. These exchanges are the hiccups previously mentioned. They break the monotony gently and then restore it, like a thoughtful pause during a long piece of music. Occasionally, a pulsar is found after a burst of activity in high-energy bands, associated with a stronger magnetic field. These magnetars remind us that neutron stars exist on a spectrum of properties defined by field strengths and rotation and interior conditions. While magnetars can be more volatile, our focus remains on the calmer pulsars whose slow fade we can readily measure across decades. The soft distinction here helps keep our evening scene free of sharp edges. Magnetars have their own stories, but tonight we are content with the stars that prefer to speak in whispers. From the ground, large radio telescopes wait patiently under the stars. Some are single dishes, sweeping their beams like large quieties. Others are arrays, fields of antennas that together mimic the resolving power of a single large aperture. The names of these instruments carry their own gentle poetry, and the places where they sit are often remote and quiet. In the small hours, when the atmosphere is still, the data flows cleanly. Pulsar astronomers watch and compare and annotate, weaving a communal tapestry from many observatories and many years. The tapestry is a record of the slow fade written in numbers and plotted as simple curves. Timelines in pulsar research are long not only in the lives of stars, but also in the careers of people. A graduate student might begin timing a pulsar and hand the thread to another researcher years later, who then adds their own length of thread. Each person contributes a stretch of care that extends the record to decades. In that sense, the human story and the stellar story share the same rhythm. They are both projects of patience. They both involve looking at the same object again and again, not expecting surprise, but discovering that the absence of surprise is itself a kind of discovery. There is a term called characteristic age that you may hear when pulsars are discussed. It is an estimate based on the current period and period derivative, assuming a certain breaking law. It is not a precise biography, but it offers a ballpark figure that situates a pulsar on the long arc of its life. Some are in their early defined region. Others are middle-aged. A few are thought to be ancient, kept spinning rapidly by their recycling and standing as quiet pillars of stability. The older the pulsar, the smaller the spin-down rate generally is, and the smoother the timing becomes. This smoothness is why the radio choir of millisecond pulsars can serve as a detector for the slowest gravitational waves. It is also why they make such good navigational aids. In the imaginary control room, the clock on the wall has taken on a soft glow. The night has deepened. Screens now display lines that record the deviation between observed pulse times and model predictions. These residuals are small, wandering to and fro like the meander of a lazy stream within its banks. Your mind follows the line without effort. It is the kind of pattern that lulls rather than demands. You are in the center of a story about steady loss, and instead of sadness, the feeling is one of ease. The star gives up its energy not as a drama, but as a quiet contribution to the emptiness around it. And in doing so, it keeps itself balanced. It keeps itself in a state that is content to be simple. There is a line in the simple models for a PULSARS emission called the death line, where the conditions for pair production and coherent radio emission might no longer be met. When a pulsar crosses this line, the radio beam would fade below detectability. This is another place where the slow fade expresses itself. It is not a cliff. It is not a sudden end. It is more like the gradual dimming of a candle as its fuel runs out. The wicks glow a little less strong each time you look, until eventually you realize that you cannot see it anymore. The star keeps turning. The lighthouse still sweeps, but its light no longer reaches your window. Between our instruments and the pulsar, the galaxy provides a broad stage. The disk holds spiral arms with denser regions and quieter ones. As the line of sight passes through these, the dispersion measure changes with direction, and with it, our sense of the pulsar's distance. In some regions, scattering is stronger, and pulses spread and smear. In others, the way is clear. This diversity builds texture into our map of the galaxy, even as we keep our particular attention on the unhurried heartbeat of rotation. The quiet variety is a gift. It means that listening in different directions yield different flavors of the same calm dish. Like noticing the way sunrise paints one valley a little warmer and another a little cooler. Each morning a variation on a theme. The slow fade is also about torque applied by currents in the magnetosphere. The radiation and the wind co-create a braking force that can be described by simple forms but refined by numerical simulations. These simulations show field lines sweeping back, forming a spiral structure that carries energy away. The entire assembly turns with the star, but has its own inertia and dynamics. The interplay is not violent. It is like the slow winding of a spool with fetier drawn outward and laid down in widening circles. Each turn of the star lays another narrow strand into the wide tapestry of space. Across vast distances, roughly uniform properties emerge. Pulsars with certain periods and period derivatives tend to have certain behaviors. Statistical studies anchor the broad patterns that our individual case studies suggest. You can think of it as listening to the same lullaby sung by different voices. Each voice has its timbre, and each offers gentle embellishments, but the melody runs through them all. Over time, the confidence in this melody increases. The field becomes a place not of surprises, but of subtle refinements. It is common for long studies to confirm what short studies suggested, perhaps with a small correction here and a small addition there, like adding a soft harmony to a familiar tune. Perhaps you would like to go back in your imagination to the moment when the star first became what it is. That moment can be thought of gently as the conclusion of a stellar life, when the core cooled into a neutron star and the rotation inherited from its progenitor was concentrated into this compact form. The birth can be told as a soft final note that created a dense remnant poised to spin for ages. From that point, the rest is the steady progression we have been tracing. The star's magnetic fields, anchored in its interior, tilt and turn. The magnetosphere organizes itself. The beam finds its shape. The surroundings breathe in the outflow and adjust. A simple beauty emerges from the interaction of rotation and magnetism, a beauty you can feel in the regular arrival of pulses as they tick through your evening, like the gentle metronome of a musician at practice. Farther along, millisecond pulsars stand as monuments to longevity. The process that spun them up, accretion from a companion, is like the long turning of a water wheel in a stream. Little by little, angular momentum was added, smoothing the sit and making it more stable. After this phase, the star becomes a more perfect clock, one that keeps time with a steady hand. The slow fade continues even then, as it must, but at a rate so small that it is measured across decades with exquisite instruments. The community of observers coordinates their efforts to minimize noise and share data. This coordination is part of the quiet craft of the field, a steady partnership that stretches across continents and time zones. At some point midway through our night together, as your body sinks a little deeper into comfort and the rhythm of the pulses softens further into the background, you may feel a pleasant curiosity drift through. Still awake? Comment the secret word nebula. If you return to the rhythm, you may sense that the slow fade is a form of keeping balance. You can imagine that the star has a small supply of rotational energy that it gives away in tiny portions, and in giving away, it maintains a kind of equilibrium. The equilibrium is not static, but it is serene. The brightness of emission depends on the current state of the rotation and the magnetic field. When one declines, the other follows suit, like a pair of dancers who never push ahead of each other but find a shared pace and stick with it. The light cylinder we mentioned earlier plays a gentle role in shaping the emission. Inside it, field lines are locked into the rotation, and near the magnetic poles, they are open, guiding charges outward. Pair production, the creation of electron-positron pairs in strong fields, is thought to fill the magnetosphere with plasma. In some models, this pair plasma is key to the coherence of radio emission. It is the background of the lighthouse beam, the medium through which the simple pulse emerges. Over time, as the star slows, the conditions for pair production change, and so the staircase of the slow fade finds another step. In reading this staircase, observers piece together how pulsar emission works, a little more with each catalog of more precise measurements. Somewhere down the line of long observation, researchers discovered that certain pulsars flip between different emission states with distinct spin-down rates. When the beam is stronger in radio, the star loses rotational energy a bit faster. When the beam is weaker or the star becomes radio quiet for a time, the spin-down rate slows slightly. This is a gentle, practical sign that the magnetosphere strongly influences the torque. Changes in current distribution alter the break. Once again, the star shows us its patience by letting us watch these changes play out over weeks and months, long enough for us to record them without hurry. You may picture one of these stars in this mode-flipping phase. In its stronger radio mode, the beam brightens a little, the pulses stand taller on your screen, and the phase of the lighthouse sweep drifts a touch more quickly as energy flows out a tiny bit faster. Then the mode switches, the beam softens or even vanishes in radio, and the spin down relaxes. The star keeps turning, and the long poem of its rotation continues. If you were plotting period against time, the line slope would tilt a little steeper for a while, then ease up. The differences are small, but the consistent association between emission state and torque invites a warm understanding. The magnetosphere is the bridge between rotation and emission. The slow fade passes across that bridge. Pulsars also teach us about space weather in our own solar system. When you time a pulsar that sits behind the sun from our vantage point, the line of sight passes through the solar wind. The extra dispersion and scattering can be measured, revealing details about the density of electrons streaming outward from the sun. Even during quiet solar periods, the patterns in the delay are clear. Thus, in listening to a distant and constant clock, we learn something about the gentle breath of our nearest star. It is a pleasing coincidence that the calm signal of a pulsar can be used to study the calm background of the solar wind as it varies with solar cycle and geometry. If you relax into the cadence of this evening, you may notice a lull nourishing your attention with small regular details. A pulsar's rotation period lies typically between milliseconds and seconds. The period derivative is typically a tiny number expressed in units per second. The implied magnetic field strength, using a simple estimate, depends on the product of the period and the square root of the period derivative. These relationships are like the bones of a simple skeleton that supports the rest of the soft tissue of pulsar phenomenology. Around them, there are specialized muscles and tendons, exceptions and refinements. But the skeleton is stable and calm, a structure you can lean on. Navigation by pulsars has already been tested on spacecraft that carry sensitive X-ray instruments, because some pulsars emit strongly in X-rays, and high-energy detectors can be compact and precise. The craft listens for the X-ray versions of the pulses, compares them to a stored timetable, and calculates its position in a way similar to how GPS receivers use satellite signals. In the deep quiet between planets, this method feels especially appropriate, drawing upon the sky's own timekeepers rather than signals from Earth. For a voyager too far out to benefit from traditional radio navigation back and forth, the stars themselves become the silent guides, flashing their patient beacons with precisely the kind of dependable pacing that gives confidence to a traveler trying to rest while coasting in the dark. Back with radio observatories on Earth, the process of finding new pulsars often involves searching large data sets for signals that repeat at constant or slowly changing periods. The search transforms the data into a form where periodicities stand out like combs with evenly spaced teeth rising above the baseline noise. When a candidate is identified, it is reviewed by eye and set aside for follow-up. The spirit of these searches is a kind of calm fishing. You cast a net of computation, leave it in the waters of the data, and then draw it back after a while to see what patterns have been caught. Most of what you retrieve is everyday static, but occasionally the unmistakable regularity of a pulsar lies there, shining quietly in the pile. This way of working is mirrored in how we round our night. Progress is not a sudden step. It is an accumulation of small confirmations. Every new pulsar adds a point to the map. Every new measure of period derivative sharpens a distribution. The slow fade of one star becomes the slow fade of a population, and beyond the population, the slow fade of the galaxy itself emerges in the sense that these stars play a role in shaping their neighborhoods and recording the curved geometry through which they move. Some pulsars sit in globular clusters, ancient spheres of stars that orbit the galaxy like small, patient satellites. The density in these clusters leads to occasional gravitational interactions that can form binaries and exchange partners among stars. As a result, globular clusters often host many millisecond pulsars. They become little cities of calm timekeepers, all spinning fast and slowing slower still, all offering their beacons with similar confidence. If you listen to one cluster's handful of pulsars and then to another's, you feel the presence of a repeated story written in different handwriting. The quiet is again the leitmotif, the gently recurring phrase. There is also the mild awareness that our instruments miss many pulsars because their beams do not intersect Earth. Statistical corrections are applied to estimate the total population. The beaming fraction is an estimate of how much of the sky is covered by a pulsar's beam, and from it, you can infer how many stars are likely spinning unseen. This is a soft reminder that the universe is larger than our line of sight, and that the slow fade plays out in more places than we will ever notice. Invisible lighthouses slow their spin within the same rules we measure for those we can see. There is a quiet comfort in knowing that the patterns you observe here have broader applicability, extending outward beyond your reach. At times, attention is drawn to the possibility of precession, a slow wobble in the orientation of the star as it rotates. Precession could cause the beam to sweep past us differently over long periods, altering the pulse profile in a periodic way. Some pulses show signs that match this idea, though the debate continues. To think of precession is to picture a top that spins not only around its own axis, but also slowly describes a circle as it leans. With a star, the angles are small and the periods long. If precession is present, it becomes another thread in the tapestry, faint and recurring, not overpowering, just another texture in the fabric. As the slow fade carries a pulsar across the death line for radio emission, the star may still be detectable in other bands, perhaps as a faint X-ray source from residual heating or magnetospheric processes. Or it may slip into a deeper quiet. The end state is then a neutron star that turns, cooled and calm, keeping its rotation in the dark where no one watches. Even this imagined final state is not somber. It is balanced. The star has given the universe a carefully measured portion of its stored spin. It holds what remains in a smooth, low hum that does not disturb anyone. One can also imagine the star's magnetic field evolving through ohmic diffusion and haul drift within the crust, processes that slowly rearrange the field on timescales long compared to human lives. These internal flows might cause subtle changes in the torque felt by the star, adjusting the slow fade's pace imperceptibly. If you consider the lines of the field like lines of gentle ink inside the star, written in a medium that allows ink to move slowly over centuries, then the changing script will reveal itself only to those who read with patience and care. The star is writing with a pen that moves almost too slowly to see, and yet the final text is legible to those who keep watch. Some pulsars act as transients, relatively quiet for long intervals, and then bright for a while. They remind us that while the overall narrative is steady, local chapters can vary their tone. Observers who monitor them keep their schedules flexible, knowing that when the star speaks more loudly for a time, there is an opportunity to learn how emission regions activate and rest. When the bright period ends, the star returns to its baseline rhythm. The variation is like a brief patch of sunlight through a cloud. It is welcome, but does not change the day's gentle weather. In terms of numbers, the angular momentum of a neutron star depends on the moment of inertia and the angular velocity. Because the moment of inertia is large, the star has a significant bank account of rotational energy in the early stages. The slow fade draws from this account, writing tiny checks every second, and the balance decreases steadily but gradually. Over hundreds of thousands of years, the decrease becomes clear. Over millions, it becomes the defining trend. There is a graceful inevitability to it, as there is to so many things composed of small, repeated steps. You could imagine a sand timer with very fine, very light grains, each grain a rotation's worth of energy gone, falling across an epoch. The sand never clumps. It slips through in a continuous stream. The radio emission mechanism, though debated, is often modeled in terms of coherent processes that require organized motion of charges along magnetic field lines. Curvature radiation, in which charges moving along curved paths emit light, plays a role, as do plasma instabilities that can amplify certain modes. The coherence needs conditions that the magnetosphere supplies when the star is within the part of the PP dot plane where radio emission is viable. As the slow fade progresses, those conditions become harder to maintain and the emission dims. There is no collapse here, only the areas lowering of a threshold until the connection is too tenuous to sustain. If you're still imagining the control room, perhaps you notice the hum of the air conditioning, the quiet patter of keys pressed gently as a new observation is logged. Down the hall, an instrument engineer leans back, sipping water, content with the clean data flowing. Outside, the dish makes a small adjustment to keep the target in view. On another continent, a colleague begins their morning shift, looking at the same pulsar from a different time zone, sharing the same sense of quiet productivity. The community breathes together, connected by the slow, steady hearts of the sky. The slow fade story also intertwines with the interstellar magnetic field. As the pulsar wind pushes outward, it can carve a bubble, a region where its own magnetic structure dominates. Where this bubble meets the interstellar field, interesting boundaries form. These are not violent shocks in our bedtime telling, but gentle gradients where energies exchange softly, smoothing differences and leaving a lingering structure that can be seen in radio or X-ray images as a softly glowing cloud. Each knot and filament is a memory of many rotations, many grains of energy given away. Look back now at the simple relation between period and its derivative. This relation lets you estimate the dipole magnetic field strength at the surface using a textbook formula. You need not dwell on the exact constants. The message is that by just timing the pulses, by measuring how quickly they slow, you can infer an aspect of the star that would otherwise be untouchable. In this way, silent listening reveals tactile facts, like learning the shape of a sculpture by running your fingertips along its outline in the dark. Astronomers do not touch the stars. They measure time. Time becomes touch. From time to time, long observations reveal correlated timing residuals across many pulsars. These correlations can be a sign of a background of gravitational waves from distant, slowly merging supermassive black holes in galactic centers. The signal is a deep murmur, rising gradually in confidence as more data is added to the pool. When it is recognized, it feels less like a fanfare and more like the confirmation of something that had been sensed for a while. Something that fits with the quiet expectations built by theory. A sea swell that was predicted is now visible as a pattern in how the boats move. The boats in this gentler version are the pulses, and the sea is space-time. The pattern is a nod from the universe that yes, the swell is there. In traveling through this field, you carry with you a sense of nested rhythms. The star's rotation is the primary beat. Around it, longer beats are made by orbital motion in binary systems. Around those, still longer beats come from precession if present, or from the gradual movement across the p-dot plane. Around all of this are the beats of the galaxy's own structure, its arms and bars and circulating gas, and beyond that, the beat of cosmic history. Each layer adds its own slow drum, and the composite is a texture that encourages your nervous system to let go, to settle into a more open and soft state. There is a little joy in placing the tiniest numbers next to the largest contexts. The small period derivative that is measured for a particular pulsar, when integrated over 1,000,000 years, amounts to a noticeable change in rotation. The tiny changes in timing arrival times caused by the Earth's micro-adjustments matter for the exactitude of a fit, and yet they are small enough that your heart does not speed up while considering them. The sense of scale helps. It tells you that there is room to relax, room for one breath to be slower than the last, without disturbing the narrative flow, room for the mind to open its hand and let thoughts drop one by one like pebbles into a pool, disappearing into smooth circles on the surface. Occasionally, an extreme case stands out. A pulsar with an exceptionally strong magnetic field might spin down quickly at first, losing a large part of its rotation energy in a shorter time. Another, with a very weak field and a very short period, might spin down so slowly that the change is barely detectable over decades. The diversity allows the field to be rich without being chaotic. Each pulsar finds its place on the slow fade timeline. In reading them, we expand not only our understanding of neutron stars, but also our appreciation for the patient variety of the universe. The environmental context includes the star's motion through the galaxy. If the star moves swiftly, its wind and the interstellar medium interact in a way that shapes a bow. If it moves slowly, the structure is different. Instruments capture these as faint arcs and tails. They are simple sculptures left by a steady artisan working at leisure. Some are curved like commas, some trail straight behind. Each is a monument to the ongoing, non-urgent outflow of energy from the star's rotational bank. You can also consider the small role of gravitational wave emission in the spin down of a neutron star. If the star has a slight asymmetry, like a tiny mountain on its surface, or a subtle distortion in its crust, it could radiate gravitational waves as it spins. For most pulsars, this contribution is minor compared to magnetic braking, but it is there as a whisper of a whisper. Searches for continuous gravitational waves from known pulsars look carefully for this signature using long observations from gravitational wave detectors. The quietness of the expected signal fits the theme. Detecting it requires the patience we have been celebrating all evening. As night slides toward morning in your imagined observatory, the data will be saved, archived carefully with metadata and checksums and logs. Later, it will be combined with data from other nights. The paper that eventually appears may be read by colleagues who understand the significance of the slight downward bend in the curve or the subtle change in spin down during a mode switch. The paper will not be breathless. It will be measured and precise. The finding will take its place alongside many like it, strengthening the collective sense of how pulsars age. In this work, the heart of the message remains the same. Rotation gives way to restful slowness in a way that teaches us about magnetism and matter and space. If you live near a place where the night is dark and clear, you might look up on some calm evening and feel the presence of these lighthouses even without seeing anything flicker. Your mind could imagine the beams sweeping over the earth, a few times each second for one, many times for another, skipping past us or brushing us gently when they align. You might feel as though the sky is a giant clock face, and the hands are invisible, but for their effect, turning the mechanisms behind the scenes. The clock does not strike. It simply continues, and in that continuing, it allows other stories to happen, including yours, here now, resting. A long-lived pulsar could potentially record in its timing history the passages of small companions, the influence of stochastic processes in the medium, the effect of solar system bodies moving along their predicted paths, and the quiet drift of its own spin. The data becomes an archive of serenity, punctuated by light variations. Reading it is like walking along a beach and noticing faint tracks in the sand. Each track has its signature, the crab's little zigzag, the smooth line of a small rolling shell, the broad indentations of a calm tide. The beach is the same beach day after day, and yet each day carries its own gentle story. Instrumental improvements continue at a stately pace. Wider bandwidths, better time resolution, more sensitive receivers, lower system temperatures. These enhancements refine our hearing. The song is the same, but we can now hear it with fewer distractions, at greater distances, with more nuance. With each gain, we find pulsars that were quiet to us before. We measure period derivatives more cleanly. The slow fade emerges from the haze with greater clarity, not as a new discovery, but as a sharpening of an old and familiar picture. In this entire meditation, there is an undercurrent of acceptance. The star will slow. It does not resist. It simply follows the path set by its properties. In this acceptance lies something like wisdom, if we allow ourselves the metaphor. The star's story is long and smooth, and it demonstrates that time's flow is gentle when one's scale is wide. A change so small it slips past our daily experience is, over eons, the author of meaningful evolution. It is an easy thing to believe and a soothing thing to internalize as your own evening lengthens and the need for sleep approaches. To bring this home, picture a single pulsar with a period of half a second and a period derivative of a small number. The pulses arrive twice each second. Over a year, the period grows by a fraction of a microsecond. Over 10 years, the cumulative shift becomes measurable enough to be a few milliseconds. Over 100 more. Over 1,000,000 years, entirely different. In watching the first few years or decades of this progression, you are participating in a much longer event that continues regardless of our attention. If you let that idea rest with you, it may comfort you to know that the star does not need us to confirm its state. We are just fortunate to witness part of the continuum. As a final image, before we turn toward the gentle closing of the night, imagine being on a coastline at night. The sea is not turbulent. It moves in broad, slow patterns. Far off, a lighthouse turns, and every few seconds a beam sweeps past, tracing a pale arc across rocks and waves. The lighthouse does not know you are there. It does what it does. The rate at which it turns is set by the gears inside, and the energy for those gears is a stored commodity, giving out slowly. Over hours, over days, you might notice that the beam comes a whisper later than before. It is still a lighthouse, still doing its work, still as reliable as any person could wish, and yet it is slightly gentler with each passing. The sea does not mind. The rocks do not mind. You do not mind either. In fact, you might find this slow, steady change invites you to breathe more deeply, to let your body adopt the same patience. The pulsar's patient spin down is an invitation for us to admire endurance, to see constancy in a world where distractions often arrive loudly. It is a reminder that quiet can be powerful, and that the long view is generous. The beam is not only a scientific signal. Tonight, it is also a soft metronome for your evening, a measured tick that validates the idea of slowing down as the preferred mode of being. Now, as the final minutes settle around us like a warm blanket, allow your awareness to return gently to the room you are in. Feel the weight of your body supported. Notice the softness of the surface beneath you and the hush of the space around you. Eyes can be open or closed. Either way, the image of the distant lighthouse can fade until it is just a kind of friendly echo. You remain safe and comfortable. The stars remain patient and unhurried in their slow fade. If this quiet journey helped you relax, we would be grateful if you subscribed and left a like, so we can keep releasing videos this often and maintain a calm corner for you whenever you need it. Rest well, feel the gentle rhythm continue, and let sleep arrive in its own soft time.